In this video, I want to have a look at some examples of differentiation from first principles. So this method of finding the gradient of the secant or of the tangent as that h approaches zero, using this is what we call differentiating from first principles. There are other methods of doing this as well, of differentiating without having to go through this whole process, but we want to do this a few times so you get the understanding of what's happening and how it relates to the gradient of the tangent and the gradient function. Alright, so let's have a look at some examples. So our first example asks us to look at the function y equals x squared. We want to differentiate it from first principles, and then we want to find the value of the derivative. All of these should have primes on them, so it should be f-3, f-5, and f-0. We want to find the value of the derivative at those three x values. Alright, so for part A, if we're trying to find that derivative, so we're going to write the limit as h approaches 0. Now, until we actually take the limit, you have to write that down in every single step. Okay, we want to have f of x plus h. So our function is x squared. So if we sub in x plus h instead of that x, we would have x plus h squared minus, and then we just want our function at x, so x squared all over h. So we're going to go through and expand it out. So we're going to leave our limit as h approaches 0. Expanding this first bracket out, you just need to be really careful that you expand that properly. So it should be x squared plus 2xh plus h squared minus x squared all over h, sorry. Now if we look at that top line there, this x squared and that minus x squared, they'll cancel each other out. So what we'll be left with is the limit as h approaches 0 of 2xh plus h squared all over h. Now, if we have a look at that, every single term in there has a h in it, at least one h, so we can go through and divide everything by h. So dividing this one will just leave us with the 2x, dividing h squared will just leave us with h, and dividing the bottom will just leave us with 1. If you get to this step and there's not a h in every single term, then you've done something wrong when you've expanded out in the working out above that. So this now becomes the limit as h approaches 0 of 2x plus h. Now when we take this limit as h approaches 0, as this number that we're adding on the end gets closer and closer and closer to 0, it gets absolutely tiny. Essentially it becomes insignificant. So what this is going to become as h approaches 0, this is just going to become 2x because we're adding something that's completely insignificant because it's that tiny. So this is our first derivative. So the derivative of x squared is just 2x. So that's part A. For part B, if we wanted to find the value of the derivative at 3, so this is another way of saying we want to find the gradient of the tangent at 3. To do that, we're going to substitute 3 in here. So we'd have 2 times 3, which is equal to 6. For part C, we want the value of the derivative at 5, which would be 2 times 5, which is 10. And for D, we want the value of that derivative at 0, which would be 2 times 0, which is just equal to 0. Now if we pull up GeoGebra, I want to show you what that looks like. I've drawn up our function f of x equals x squared in GeoGebra, and I've got a point here. Now, wherever that point is, I want to find the gradient of the tangent at that point. That's what my derivative is. So if I draw in the tangent to the line at that point, we can have a look at how its gradient changes. So as we move further up here, you can see the gradient of that red line is getting steeper, so our gradient's increasing. As we come down closer to 0, our gradient is decreasing. And if we moved into the negatives, then our gradients would actually become negative as well. So if I figure out the gradient of that line, so I've just drawn in there, it's drawn a right angle triangle, and this is the gradient of the line at this point. So if I move it up to, I think our first point was 3 that we subbed in, so if I get that as close to 3 as I can. Don't know if I can get it perfect. No, not quite. But I can get it to 3.01, and that has a gradient of 6.01, so that's pretty close to our 3 and 6 that we actually figured out. If I pulled it up to 5, you can see that my gradient is increasing. And it's gone off the screen there, but you can actually read that the gradient there is 10, which is what we found, which makes sense because the gradient has to be bigger. And right down here, our last one that we figured out was 0. And if we have a look at that there, the gradient at 0 is just 0, and that's because the tangent is perfectly horizontal at that point. Our second example is slightly more complicated. So the function we're given this time is x squared plus 4x. For part A, we are just asked again to differentiate from first principles. So f dash x will be equal to the limit as h approaches 0 of f of x plus h. So that means it's going to be x plus h squared plus 4x plus h. So anywhere there was an x, I've replaced with an x plus h. And then I'm going to subtract whatever our original function was, which was x squared plus 4x. Now, do put your brackets in around there because otherwise you might get mixed up with your negative that has to apply to everything in there. And that's all over h. Now, if we go through and expand the numerator, we're going to have x squared plus 2xh plus h squared plus 4x plus 4h minus x squared minus 4x. And again, that's all over h. Now that x squared will cancel out with this x squared here, and my 4x will cancel out with my 4x here. So what we have left is the limit as h approaches 0 of 2xh plus h squared plus 4h all over h. Now remembering again that there should be h's in everything, so we can cancel them out in this step. So we can cancel all of those h's out, and that's going to give us the limit as h approaches 0 of 2x plus h plus 4. Now, as that h gets tinier and tinier as it approaches 0, this term in the middle here becomes insignificant. So that's just going to become 2x plus 4. So that is our first derivative. Now, part B of the question asks us to find the gradient of the tangent at the point 1, 5. So that's just asking us to find the value of the derivative at this point. So our x coordinate there, our x value is 1. So it's asking us to find f dash of 1, which would be 2 times 1 plus 4, which will just give us 6. Let's have a look at one more example. It's asking us to find the value of the derivative at minus 1 if f of x is equal to 3x squared minus 1. So the first thing we need to do is find the derivative. So we're going to take the limit as h approaches 0 of 3 outside of x plus h squared minus 1 minus 3x squared minus 1. So that's our f of x plus h minus f of x, and that's all over h. If we go and expand that out, we're going to have the limit as h approaches 0 of 3 outside of x squared plus 2xh plus h squared minus 1 minus 3x squared plus 1 all over h. Now going through and expanding that one last bracket, we've got the limit as h approaches 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 over h. And now we want to cancel things out, so my 3x squareds cancel and my minus 1 and plus 1 cancel. So that's going to give me the limit as h approaches 0 of 6xh plus 3h squared all over h. Now my h's do cancel again, and this time I'll be left with the limit as h approaches 0 of 6x plus 3h. Now this time as h goes to 0, we're timesing it by 3. But if we times something that is a 3 or any number by another number that is really, really, really small, really close to 0, then that product is still going to approach 0. It's still going to become insignificant. So this whole 3h this time will go to 0. So we'll just be left with 6x. Now what the question actually asked is we want the value of that derivative at minus 1. So we're going to substitute in minus 1, which would just give us minus 6 as our answer. Now all of the examples that we've looked at in this video have had x squared terms in there. You can do this with most functions, but you can imagine that the more complicated the function gets, the more complicated the algebra in the middle gets as well. So you often won't be asked anything above, say, a cubic where it's got a power of 3 on there, because otherwise it does get a bit messy. But we can use it for higher powers as well. So that's having a look at some examples of differentiation from first principles.